Morning, guys. Welcome back from spring break. I hope you had a good one. It's probably extremely boring. I didn't do much. I resurrected my Tamagotchi, so that was fun. Yeah, I baked a pie. I don't know what else. Nothing too exciting. Today we're going to jump into Unit 7, which deals with equilibrium. There will be some math in this, not too much with this chunk of units, but later on we will be doing more math, and those basically involve equilibrium constants and reaction quotients. So we'll kind of be learning those formulas today. So the idea behind equilibrium is that reversible reactions do and can occur. So early on, when you're younger, a lot of science teachers define chemical reactions as things you can't easily change back, whereas physical reactions, you could easily change it back to what you started with. I don't like that definition because a lot of chemical reactions you can do the reverse reaction. It's just that you have to put in more energy or more reactants, heat, something to make that reverse reaction occur. So chemical reactions are not necessarily permanent. So two examples. The first one is kind of like it's a chemical equation for a physical process, the evaporation, condensation of water. So our reactants and products are the same kind of material, it's just they're in a different phase. So going from liquid to gas and gas to liquid. Another reaction is dissolving and precipitating a salt, which, remember, this kind of chemical reaction is both a chemical process and a physical process because we break ionic bonds and we change intermolecular forces. So that points to a chemical and physical process. But we can dissolve a salt in water, go from solid salt to aqueous salt. But we can also go from aqueous salt to solid salt by evaporating water. So by applying heat, we can basically get rid of all the water in the aqueous solution, and we are left with a sodium chloride solid. You can also think about when we did the precipitation reaction, you both created a solution. You went from a solid of your two reactants to an aqueous solution of your two reactants, and then you added those two aqueous solutions together to precipitate out a new solid. So these reactions are reversible. There is also the absorption and desorption, which is the opposite of absorption, of a gas, and this is also a reversible process. So going from the first image to the second image, right here the gas particles are at equilibrium, so as much gas particles as possible are dissolved in the solution. But if we apply pressure, we can basically force more gas molecules into that solution by increasing that pressure, so the solubility of the gas increased. So when the pressure applied is small, the concentration of gas in the water is relatively low, but we can put more pressure on to increase the concentration of the gas, so the solution has a higher concentration. These are both reversible, so we can also start with this image, P2, decrease the pressure, and we would notice gas coming out of the solution. So this can kind of be applied again to like soda solutions, like how they make soda, is that they basically force CO2 gas into a beverage containing mostly liquid to make a carbonated beverage. So beverages can be carbonated by increasing the partial pressure of CO2 on the surface of the liquid. That's why the containers of pop, whether it's a can or a 2-liter, they are pressurized containers. So there is an increased pressure there forcing the gas into the solution, which is why if you look in the 2-liter, you don't see any bubbles before it's opened. So remember, solubility of gas is directly proportional to the pressure of the gas on the surface of the liquid. Usually with soda, that pressure of CO2 in the bottle is about 4 atmospheres. And then when you open the bottle, you're basically decreasing that pressure. It drops to about 3 times 10 to the negative 4 atm, so 0.0003 atmospheres. which is about the pressure, partial pressure of CO2 at sea level. So since the partial pressure decreases, the gas is less soluble in water, so you start to see bubbles come out of the solution, and that's the desorption of CO2 gas in a carbonated beverage. So when the lid is removed, the partial pressure of CO2 decreases, and the gas starts to leave the solution. And then from here, we kind of see two reactions, so CO2 and H2O going H2CO3, and then we go to H plus and HCO3. So when CO2 dissolves in water, it reacts to form carbonic acid. That's why with global warming and everything, you might hear about the acidification of the ocean. So if there's increased CO2 in the atmosphere, that increased concentration increases the pressure of CO2 on the ocean, which then means that more CO2 actually dissolves into the ocean. So that's how the ocean kind of becomes acidified, which is really bad for coral reefs because they are basic, and then that acid basically breaks down that coral, which is bad. So then the carbonic acid does dissociate to form H plus and HCO3 minus. The HCO3 minus bonds with the H plus to form H2CO3 again before becoming gaseous CO2 and H2O. So that's why we have kind of a two-step reaction here. Reversible reactions are also applicable in biology a lot. So in your blood, you have hemoglobin, which is a protein, and this is basically what carries oxygen through your blood to your organs and everything so that it can function. So in your lungs, you do have blood vessels, and you have these little pockets called alveoli. The hemoglobin does not, that is not bonded with oxygen, flows through your blood to your lungs, and then it grabs onto this oxygen to make this hemoglobin oxygen complex. Then oxygen is later released to cells within the organism, so that blood goes from your lungs to your other organs, skin, etc., and then can release that oxygen to your cells for them to function. And this is an ongoing process, so both of these reactions are occurring at the same time. It's like a flow. We also have reversible redox or oxidation reduction reactions, and this is applicable for batteries especially. So when you use your phone during the day or your Chromebook, you're discharging a battery. Maybe it's lead acid, probably not. But same idea, no matter what kind of battery you had, lithium ion or whatever. So the discharging using your battery produces electrical energy for your device to actually function. So your device is using this energy that is produced to power your machine. And then at the end of the day, when your phone battery is low or your Chromebook is dying, you have to plug in that to an outlet, which then takes electrical energy from the outlet in the wall, the wires, to then produce these reactants for your discharging to occur the next day. So recharging process requires an input of electrical energy. You can't just leave your phone on your bedside table and expect it to spontaneously recharge. You do have to input energy. So this reaction is reversible. It's not a permanent change. We also have reversible acid-base reactions, and we've especially seen this with our weak acids and weak bases. So both of these reactions above involve acetic acid, which is CH3COOH, and water. And they take place at the same time in any bottle of vinegar. So if you just have a little bottle of vinegar, some of the acetic acid reacts with water to produce HCO3OO-, the conjugate base, and water's conjugate acid. But at the same time, you have the conjugate base of acetic acid and H3O+ reacting to produce acetic acid and water. So both of these reactions are taking place at the same time. It's not like one completes and then the other goes. They're going back and forth. So usually in class, like in-person classes, what we would do is an activity where we have two people. One person represents the forward reaction, so these reactants go into these products, and one person represents the reverse reaction, the products going back to your original reactants. And then we would have basically a bunch of scrap paper balls. And these students would basically compete throwing paper balls back and forth to one another. So they are restricted. For example, they can only use one hand and they can only throw one ball at the same time. So usually what we see occurring, even if we start with a bunch of balls on one side and only a few paper balls on the other side, eventually what happens, because they're throwing basically at the same time, that would be basically equilibrium. So both reactants are reacting, whether it's the forward reaction or the reverse reaction, and they happen at the same time. So what happens is we end up with the same concentration of paper balls on either side, and that is equilibrium. So chemical reactions don't just go to completion and stop. Usually the reverse reaction starts going, and they go back and forth until eventually they reach the same rate. So usually to simplify things, we do write the chemical equation with a two-way arrow. Rather than say we have one reaction and another reaction, we combine it and use our two-way arrow. So that's why with weak acids and weak bases, we always put that double arrow in the middle to show that both reactions are occurring. So some reactions do go to completion. Not all have that back and forth arrow. Typically with strong acids, we might have a little bit of a reverse reaction going on, but overall we have a pretty strong one-way reaction. Another is with the burning combustion of like methane, CH4. When we produce CH4 and O2, we get CO2 and H2O. The CO2, carbon dioxide, and water don't really go back into CH4 and O2. It's a one-way process, so we use a one-way arrow. We don't see this happening naturally, the reverse reaction. So for these reactions, again, one-way arrow is used. But some reactions, most, do not go to completion. So all reactants do not get used up. The system reaches what we call a dynamic state, where reactants are continually returning into products, and products are continually turning back into reactants. So that dynamic state is what we call equilibrium. And for these reactions, we use a two-way arrow. So the two-way arrow tells us that the reaction is proceeding in two directions at the same time. It's not just one and then another. It's at the same time. There's a forward reaction where N2O4 is converted to 2 moles of NO2, and a reverse reaction where 2 moles of NO2 is converted into N2O4. We can show this graphically. So here we have on the y-axis the concentration in moles per liter or molar over time. So here with the forward reaction, we're starting with a concentration of N2O4, which is the blue line. That's why we have some defined concentration there. And we start with no NO2, which is why the red line starts at 0. This is occurring in a closed system, like a jar with a closed lid, so there's no interaction with the outside surroundings. It's only the system. So that's why the concentration of N2O4 decreases over time. So it becomes used to produce 2 NO2. So we see the concentration decreasing for N2O4. Meanwhile, at the same time, the concentration of NO2 is increasing. And you might notice, remember when we did rate law and things like that, the slope of these changes basically have twice the amount of NO2 forming as we have N2O4 disappearing. And that's because of the stoichiometric coefficients. So that's why the slopes are different. As time goes on, again, N2O4 drops while NO2 increases. And as 2 moles, again, of NO2 are created, we are losing 1 mole of N2O4. And eventually we end up with this straight line, where over time the concentration isn't really changing for our reactants and products. At this point, the system has reached equilibrium. So at time, whatever this is about here, I would estimate, is where the slope stops changing. At this time, that's where the system reaches equilibrium because the concentrations of NO2 and the concentrations of N2O4 are not changing. Both reactions are occurring at an equal rate.